Good morning. I'm going to show some results about the ocean atmosphere mechanisms explaining the heat buildup in the Western Pacific that leads to El Niño events in an ensemble of ocean reanalyses. This is the typical picture of the composite of El Niño events. It corresponds to the Equatorial Pacific. We have depth, we have longitude. For three different lags, the shading corresponds to temperature, and the contour corresponds to the tendency in temperature. At zero lag, we have the typical structure of an El Niño event. And about 1 to 2 years before El Niño events, we have on average, these La Niña-like conditions with subsurface warming in the Western Pacific subsurface, and also the tendency towards the warming of the Central Pacific at the level of the thermocline, which later turns into the recharge phase in equatorial heat content. Here in this talk, I'm going to focus on this time lag, and I'm going to describe the spatial variability of the oceanic mechanisms that explain this heat buildup in the Western Pacific. To this aim, I'm gonna, I have used 5 different simulation products. This is the list of the reanalyses. All the figures correspond to the average of these products, but I'm gonna focus on those anomalies that show the same sign for all the data sets, and this is shown by this stippling. All the figures correspond to the average of the 11 El Niño events in this period, in 1961-2008, and they only show the interannual component after filtering out the higher frequencies. We've seen that the growing phase, that the warming in the subsurface warming in the Western Pacific is associated with La Niña-like conditions. So here I'm showing again for the Equatorial Pacific, this is depth, this is longitude, the climatological picture of the horizontal divergence. For all years, the average for all years, the average for La Niña years, and the difference between La Niña years minus all years. The arrows correspond to the zonal and the vertical velocities. The climatological picture shows that the well-known horizontal convergence in blue in the Central and Eastern Pacific, the upwelling motion, and the Ekman divergence in the surface. There is no strong signal in the Western Pacific. During La Niña years, the anomalies in the Central and Eastern Pacific are stronger, as we expect, but we have this kind of cross-shaped pattern in the wormhole with horizontal convergence in blue in the surface, downwelling motion and divergence, horizontal divergence at the subsurface at more or less 100, 130 meters depth. This can be seen more clearly in the anomalies. We can decompose the horizontal divergence into the zonal and the meridional divergence, and here I'm going to focus on these two vertical, these two longitudes, and I'm plotting the vertical profiles of horizontal, zonal, and meridional divergence. In red, we have the zonal divergence. In blue, we have the meridional divergence, and in green, the horizontal divergence. Close to the dateline here, we have, the same anomalies, the same sign of anomalies in the zonal and meridional component. As we know, we have divergence, zonal divergence, meridional divergence, and so horizontal divergence. In the subsurface, we have the opposite sign, so the upwelling. But in the far Western Pacific, in the core of the wormhole, we have again the meridional convergence, but the zonal component is different and is stronger than the meridional signal. And so we have horizontal convergence in the surface and horizontal divergence at the subsurface. This different, this vertical distribution of horizontal divergence and also of the downwelling and, well, the vertical motion determines the heat advection in the different behavior of heat advection in the two areas. Here again, it's the Equatorial Pacific. This corresponds to the growing phase of the subsurface warming in the Western Pacific. So we have, well, the first panel, panel A, corresponds to the anomalies in that phase of the oscillation with, well, the shading corresponds to temperature. We have growing La Niña-like conditions. And the other panels correspond to the different advection terms. The shading is the heat advection, either it's zonal, meridional, or vertical. And the contours correspond to the tendency. The contours are the same in all the plots. And we see in panel B that together the zonal, meridional, and vertical, they explain a large fraction of the tendency in the warming and also in the cooling. And if we decompose this heat advection in the three different terms, we see that the vertical advection is the only one that is having a significant contribution in the core of the whirlpool. The zonal and the meridional components, they do not contribute to this area. Instead, to the east of the dateline, we have a contribution. Here is zonal and vertical together, and they explain a large fraction of the tendency, and also we have this component from the meridional advection. Here, this is the equator, so in the off-equatorial regions, this meridional advection is stronger. So to see this meridional dependency of the heat advection, I'm here also showing the meridional transects in these two areas in the Western Pacific and close to the dateline. Again, they are the same plots, the same variables. This is the whirlpool, the core of the whirlpool. We see the downwelling motion from more or less 10 south to 8 north, and that explains this vertical advection, and this vertical advection explains a large fraction of the subsurface warming, and the other factors, they don't have a significant contribution. On the other side, we have a completely different picture in just 20 degrees to the east of the core of the whirlpool. We have this enhancement of the shallow meridional overturning cells with upwelling at the equator, Egmont divergence in the surface, downwelling in the off-equatorial regions at about 5 south, 5 north, and meridional convergence close to the thermocline, which is represented in green. Again, we have a close correspondence between the three terms of the heat advection and the tendency. And if we decompose this advection into the different terms, we see that first, the off-equatorial, the convergence, the meridional convergence explains a fraction of the subsurface warming close to, above the thermocline, but also we have the role of the intensification of the equatorial undercurrent, which explains the warming near the equator at deeper depths. To summarize, we've seen a sharp transition between the anomalies in the core of the whirlpool and close to the dateline. In the whirlpool, we have surface zonal convergence and downwelling, and the role of meridional advection is weak. Near and to the east of the dateline, we have instead surface convergence and subsurface convergence and upwelling, and the role of advection is due to the three components, due to the intensification of the equatorial undercurrent and the shallow meridional overturning cells. Thank you.